Welcome back to the deep dive. Today we're tackling a really critical issue for global food security, actually. We're diving into a 2021 paper, Conservation Risks and Portfolio Effects in Mixed Stock Fisheries, led by Jonathan W. Moore and colleagues. Our mission really is to unpack this thing and figure out how the sheer complexity of fish biodiversity, helps and hurts our ability to fish sustainably.
It's absolutely vital. I mean, think about the scale here. You've got, what, over 32,000 fish species, and they provide something like 15% of the protein for, gosh, over 4.5 billion people globally. So yeah, fish biodiversity is fundamental to keeping the world fed, but the paradox, the one this paper really digs into, is that this diversity offers resilience, yeah, but managing it, that takes systems way more sophisticated than what we often have.
Okay, right. So let's unpack that paradox, that central conflict. The paper focuses on mixed stock fisheries. These are systems where you're targeting multiple populations, sometimes even multiple species, all at the same time. We kind of assume biodiversity is just good for the ocean, good for the ecosystem. But you're saying in this mixed stock scenario, it actually creates this built-in risk, something they call mixed stock overfishing, hashtag I, the dual nature of biodiversity in fisheries.
Precisely. Let's start with the upside, though, because it's crucial. It's this thing called the portfolio effect.
Hmm.
It's a concept they've actually borrowed from financial economics.
Okay, like investing.
Exactly. If you have a financial portfolio, you don't put all your money in one stock, right? You want assets that fluctuate kind of differently, asynchronously.
Hmm.
So when one's down, maybe another's up. It smooths out your overall return over time.
That statistical averaging makes sense for money, but how does that translate to, fish populations?
Well, in the marine world, it means if you're harvesting multiple fish populations, multiple stocks, whose dynamics are asynchronous, meaning their boom and bust cycles happen at different times, unpredictably, then the aggregate catch, the total amount of fish you actually land, becomes much more stable from one year to the next.
Ah, okay. Like having different crops in a field. Bad year for corn, maybe the wheat does okay.
That's a great analogy. The wheat or the beans might thrive and save your overall harvest. That stability, that predictability, that's the core benefit biodiversity offers a productive fishery.
So we rely on this mix, this asynchrony, for stable catches. But you mentioned it also creates a conservation dilemma. How does the very thing giving stability also introduce risk?
Yeah, that's the rub. The problem comes up because often managers aren't targeting each individual stock, each crop perfectly. They're often targeting the whole mixed field, the aggregate. And the paper highlights 4 key dimensions of biodiversity that really control how intense this trade-off gets.
Okay, what are they?
First, there's richness. That's simply the total number of distinct stocks in the mix.
More stocks, more diversity. Got it.
Second, evenness. This is about how the total biomass, the total fish weight, is distributed among those stocks. Is it spread out evenly, or does one big stock dominate,
Yeah.
making up like 99% of everything? That would be very low evenness.
Okay.
Third, asynchrony, or correlation. How independent are their population cycles? Do they all boom and bust together, or do they fluctuate pretty differently? High asynchrony means they fluctuate differently.
Right, the portfolio idea again.
Exactly. And fourth, heterogeneity. This is about differences in their basic productivity, their intrinsic ability to reproduce and bounce back from fishing pressure. Some stocks are naturally just more productive than others.
That last one, heterogeneity, that sounds like where the vulnerability really creeps in. If you're fishing a mixed bag and your overall strategy is based on the total amount or maybe geared towards the most productive stocks, what happens to little guys? The ones that are naturally weaker or reproduce more slowly?
They get hammered.
Basically, yeah.
The overall harvest rate that works for the big productive stocks is inevitably way too high for those less productive, weaker component stocks hidden within the mix. You're essentially setting up a system that, well, it almost guarantees the depletion, maybe even the local extinction extirpation of those weaker stocks.
Wow.
And this mixed stock overfishing, it doesn't just hurt those stocks. It actually compromises the fishery's overall long-term yield and stability, even if the total catch looks okay in the short term.
Okay, so to really get a handle on this, the researchers used simulations, right? They modeled these mixed stock fisheries to map out the relationships between those biodiversity dimensions and what were the key outcomes they measured?
They looked at 3 main things: catch stability, how consistent the harvest is year to year; total yield, the overall amount harvested long term;
Yeah.
and biological risk, which they measured as the probability of driving a stock locally extinct or extirpation.
And what did they find in their sort of base case scenario where management didn't have much ability to target specific stocks? Low control.
Well, the results were pretty stark. They really showed how biodiversity acts like a double-edged sword in this situation. So in that low-control base case, fisheries that had high stock richness and high asynchrony, the most diverse in that portfolio sense, they did show much higher catch stability, like over 2 times greater than the less diverse systems. So that stability benefit is definitely real.
Okay, so the portfolio effect works for stability. But where's the trade-off? What was the cost?
The cost was, well, it was immediate and pretty substantial. Under that exact same low control scenario, the very thing delivering stability, that high asynchrony, also jacked up the probability of wiping out the weak stocks to around 15%.
The 15% risk of extinction for some stocks.
Yeah, just as a baseline. And here's the other kicker. Increasing richness and asynchrony, while boosting stability, also generally lowered the total potential long-term yield you could get, sometimes by as much as 25%.
Huh. So you trade volume for stability, and you take on a big conservation risk while doing it. That's not ideal.
Not ideal at all. And that risk got way worse if you had low evenness in the system.
Right, that's where one or two stocks just dominate everything else.
Exactly. Unevenness turned out to be a really critical amplifier of risk. In simulations where just one stock made up, say, 99% of the total production, that's extremely low evenness.
Right.
The extirpation risk for the other, smaller stocks could shoot up as high as 40%.
40%, that's incredibly high.
It's catastrophic, functionally, especially when combined with those asynchronous dynamics.
Mhm.
Basically, the huge dominant stock masks the collapse of all the little guys hiding underneath it.
Wow. Okay, so it really sounds like the main takeaway from the simulations is that you can't just look at the total catch anymore. These different facets of biodiversity, asynchrony, richness, evenness, they all interact in complex ways, and they force this really brutal trade-off between stable catches, high yield, and conserving all the pieces.
Right. And that leads directly to the next big question the paper tackled. Okay, if this trade-off is inherent in diverse, low-control systems, how do you break it? How do you get the benefits without the costs? They looked at 2 main management levers you could pull. In the paper's terms, they called them P-star, PU, and C-star C.
Okay, let's translate P star and C star into plain English.
Sure. P basically represents risk tolerance. You can think of it as how hard managers are willing to fish, how close to the edge they push things to maximize yield. A lower P means fishing less intensely, being more cautious. And C represents management control. This is the big one. It's the capacity to actually know which specific stock you're catching and to adjust your fishing effort accordingly. High control means you can target harvest very precisely.
Okay, 2 levers. Fish less hard or fish smarter. Let's look at the first option, just reducing the overall fishing pressure, lowering P. Does that work to reduce the conservation risk?
It does work, yes. If you fish less hard overall, you reduce the pressure on the weak stocks. But the economic and social sacrifice involved is potentially huge. The simulation showed that in those highly diverse asynchronous systems, if you wanted to cut that extirpation risk dramatically, say, from a dangerous 18% down to a much safer 3%, you had to accept a massive 50% reduction in the total harvest.
A 50% cut in yield.
50%. Cut your harvest in half. Think about what that means for fishing communities. Half the jobs, half the revenue, half the food potentially coming out of that system. That kind of sacrifice makes just lowering P really, really difficult politically and economically. It's often not a practical solution on its own.
Right, so that points towards the other lever. Increasing management control, boosting C, that sounds like the more desirable path.
That's the unequivocal finding of the paper, yes. Increasing management control is presented as the optimal solution. And control here means having the tools and the information to allocate harvest precisely. Things like closing certain areas to fishing temporarily, restricting fishing during specific run times when vulnerable stocks are present, or maybe even using rapid genetic stock identification in near real time to know exactly what fish are being caught and adjusting harvest on the fly.
And what was really striking was how effective even small improvements in control could be.
Absolutely. The simulations show that even moving from zero control, basically fishing blind with respect to stock composition, to having just 25% of your harvest decisions informed by stock-specific data, that alone slashed the extirpation risk by at least half, often more.
Just a quarter bit of information makes that much difference.
A huge difference. And under scenarios with complete management control, where managers hypothetically knew exactly which stock they were catching and could target perfectly anew, conservation risks basically dropped to near zero. Even when they were pushing hard for high yields, a high P, And crucially, high control didn't just eliminate the risk. It actually increased the overall fishery yield and stability compared to the low control scenarios.
How did it increase yield?
Because managers could then fully and safely harvest the abundant productive stocks without worrying about wiping out the weaker ones. They could let the strong stocks produce maximally while protecting the vulnerable ones.
So high management control fundamentally breaks the trade-off. It allows fisheries to actually get the stability and yield benefits from biodiversity while conserving it at the same time.
Exactly. It avoids that brutal choice between exploitation and conservation.
Okay, so this is where the theory gets tested against reality. The researchers didn't just rely on simulations, they looked at real-world examples. They applied this framework to three major sockeye salmon fisheries up in the eastern North Pacific.
That's right. Bristol Bay in Alaska, and then the Fraser River and the Skeena River, both in British Columbia, Canada.
And these are kind of perfect test cases, aren't they? Because they're all these big, complex, biodiverse salmon systems, but they differ quite a lot in how much management control they actually have.
Precisely. Bristol Bay is generally considered a system with relatively high management control. The Fraser may be medium control, with lots of historical challenges. And the Skeena, traditionally, has had lower control, and it also happens to have the lowest evenness among its sockeye stocks, more dominated by a few larger runs.
So how did the researchers compare the outcomes in these different systems using the lens of their model?
They looked at the status of individual salmon stocks within each system over time, specifically comparing the 1980s to the 2000s. They used these technical metrics, UMSY and SSMSY, to see how each stock was doing relative to its targets for maximum sustainable yield, or MSY.
Right. UMSY tells you if the fishing rate is sustainable, around 1, too high, over 1, or too low, under 1. And SSMSY tells you if the population size, the spawning stock, is healthy, around 1, or depleted, below 1. Ideally, you want all your stocks clustered right around UMSY equals 1 and SSMSY equals 1.
Exactly. You want them right in that sweet spot. And when you look at the data for Bristol Bay, the high control system, it's pretty remarkable. Their individual stocks over the decades they examined were generally tightly clustered right around those optimal targets, UMSY near 1, SSMSY near 1. It really looks like a system that's successfully balancing multiple objectives, getting good yield while keeping stocks healthy and minimizing risk, pretty much like the high control simulations predicted. It's kind of the poster child.
Okay, the poster child for high control. Now, contrast that tight picture with the Canadian systems, the Fraser and the Skeena, with their medium to low management control. What did their stock status plots look like?
Much, much messier. Lots more variability between individual stocks and big shifts over time reflecting changing management priorities. For instance, if you look back at the Fraser River in the 1980s, the priority was often maximizing catch, and you saw many individual stocks being fished really hard with UMSY often well above 1, and consequently, many stocks became severely depleted, SSMSY way below 1.
So, overfishing was happening on specific stocks within the mix.
Clearly. Then, fast forward to the 2000s, there was a major policy shift towards prioritizing conservation, partly driven by those past depletions and maybe listing concerns. So managers drastically cut back the overall harvest rates. The average UMSY across Fraser stocks dropped significantly, from about 1.30 in the 80s down to around 0.56 in the 2000s. That's a big reduction in fishing pressure overall.
Okay, so they sacrificed harvest. Did that lead to the recovery of those depleted stocks? Did SSMSY bounce back towards 1?
Well, that's the tough part. Unfortunately, not really, or at least not consistently or fully across the board. This really highlights that double bind you get with low control. By cutting the overall harvest rate so much to protect the very weakest stocks, many of the stronger, more productive Fraser stocks ended up being significantly underfished. Their UMSY was way below 1. That represents potentially millions of fish in lost harvest, lost economic opportunity.
So they lost yield from the strong stocks.
And yet, many of the weak stocks still failed to fully recover their abundance. SSMSY stayed low. And this was likely due to factors beyond just fishing pressure at that point, things like poor ocean survival conditions during that period, or maybe ongoing habitat degradation within the Fraser watershed itself. Similar patterns were seen in the Skeena, too.
So it seems like low management control really forces managers into this difficult, almost lose-lose situation. You either risk fishing the weak stocks into oblivion if you push for yield, or you sacrifice huge amounts of potential harvest from the strong stocks if you prioritize conservation. And you might still not get the recovery you want for the weak ones if other factors are limiting them.
That captures the dilemma perfectly. Without the ability to fine-tune harvest based on individual stock status, you're constantly making these broad-brush decisions that are suboptimal for almost every component of the system. Hashtag tag V. Broader implications and future research.
Okay, thinking broader now, what are some of the bigger implications of this work, maybe for society or for how we think about fisheries management generally?
Well, one really critical societal implication, especially relevant for salmon, involves enhancement practices like hatcheries. Hatcheries are often implemented with the goal of boosting the productivity of certain stocks, maybe compensating for habitat loss, or just increasing the total number of fish available for harvest.
Right, make more fish. Sounds good.
But here's the potential ecological trap. By creating one or two hyper-productive hatchery stocks, you often drastically reduce the evenness within the overall salmon complex. You end up with these massive hatchery runs alongside smaller, wild, potentially less productive populations.
Ah, and we saw in the simulations that low evenness dramatically increases the conservation risk for the non-dominant stocks, especially if their dynamics are asynchronous with the big hatchery runs.
Exactly. So enhancement, while seemingly beneficial for overall numbers, can actually exacerbate the conservation challenge for wild biodiversity. It makes sustainable management even harder unless you also simultaneously increase your management control to protect those wild stocks specifically. It increases the need for that sea star.
That's a really important point. No, we should also probably acknowledge some of the complexities or limitations when comparing those real-world case studies, right? It's
Yeah.
not just about management control.
Absolutely. The paper acknowledges this too. Comparing Bristol Bay, Fraser, and Skeena isn't perfectly clean. They have different histories, different underlying habitat quality. Bristol Bay's spawning habitats are generally considered more pristine than large parts of the Fraser and Skeena. That affects stock productivity regardless of fishing.
And didn't you mention something about how they define management units?
Right, the scale is different. In Bristol Bay, the management units they track are often geographically larger, potentially grouping several distinct spawning populations together. In BC, the tendency has been to define management units at a much finer scale, down to individual tributaries sometimes.
So it's possible that Bristol Bay's apparent success at the aggregate level might be masking some weaker stock issues happening within those larger units, while the BC systems, by looking finer, are revealing problems that might exist everywhere.
It's certainly possible, yeah. That difference in monitoring resolution complicates direct comparisons. But even with those caveats, the overall pattern holds.
Yeah.
The system with demonstrably higher capacity for control seems to be navigating the biodiversity trade-offs much more effectively.
Okay, so looking forward, what does this research suggest about future directions for management, especially in these complex, biodiverse fisheries?
Well, the core message really boils down to two paths, as we discussed. Either you need to extract significantly less overall, except lower yields, or you need to regulate much, much better by increasing control. Regulating better points toward strategies like focusing harvest in localized terminal fisheries, catching salmon closer to their home rivers where you have a better idea of which specific stock you're intercepting.
Instead of catching them all mixed together out in the ocean.
Precisely. It also points towards investing in and implementing dynamic management, things like temporary spatial or temporal closures that can be adjusted based on real-time data. A key part of that is improving our ability to rapidly identify stock origins, maybe through genetics. So those harvest decisions can be made almost moment by moment during the fishing season. Hashtag tag outro.
This has been a really insightful deep dive. It feels like the core integrated message here is pretty clear. Biodiversity in our fisheries, it's not just nice to have. It actually provides fundamental resilience and stability. That's the upside.
Yeah.
But actually capitalizing on those benefits, getting that stable food source without inadvertently destroying the underlying resource base, especially the weaker components, that seems to absolutely require a high degree of what the paper calls management control. It's about having the capacity, the information, and the tools to make nuanced decisions about the specific brief of the system, not just managing based on the aggregate total.
That sums it up perfectly. Control unlocks the potential of biodiversity. Without it, biodiversity becomes almost as much a liability as an asset from a management perspective. And maybe just a final thought for you, the listener, to chew on. We know we need to feed a growing global population, right? And we know climate change is making marine ecosystems more volatile and unpredictable. So faced with that reality, where should societies prioritize future investment? Should we pour resources primarily into things like large-scale habitat restoration, trying to boost the intrinsic productivity of all stocks, make them all stronger? Or should the focus be more on investing in the cutting-edge monitoring technology, the genetic tools, the sophisticated governance systems needed to achieve near-perfect management control, allowing us to better utilize and conserve the diversity we already have. This paper strongly suggests that continued, perhaps even increased, investment in really understanding, characterizing, and actively managing for the biodiversity within these critical fishery systems is going to be essential for navigating the future.